All right, we're on. All right, so this is something that I've been teaching for many, many, many years. And many of you have already learned it. How many people have learned the light spectrum? Okay, you've heard of that. Red, you haven't heard about it? Never? You did raise your hand. I'm sorry. My apologies. Excellent. So everybody's heard about the light spectrum. Okay? Now, what do I mean by light? Do I mean light that we use to illuminate objects? Is that what I mean by light? Is that what light is, Will? There are different kinds of light. I like that. What does that mean, there are different kinds of light? There's UV. What does UV stand for? Ultraviolet light. What else? Different kinds of ultraviolet, A, B, C, depending on its intensity. I like that too. What else? What is it? Gamma rays is a form of light. Anybody else have a form of light? Maybe two more types? Antoine? No idea? Yes. Infrared? Yeah, infrared light. One more. Radio waves. Okay, good. And we have the light. This is like the spectrum. Okay. Light has structure. It's a wave. It can also be viewed as a particle, but we're going to look at it today as a wave. Okay. Let's say that's the x-axis. Excuse me, it has crests. I like that. This is a crest. This is a trough. Unless you're upside down, then that's the crest. And then what? This is what? Where it changes direction. That's the node. Okay. What's the wavelength? That's the wavelength, the distance between two crests. Yes? What else? What is it? I can't hear you. Amplitude. I like that. Amplitude. Yes. This is the amplitude. Let's make it that black so you can see it. This is amplitude here. Amplitude is not from the crest to the trough. Amplitude is from the nodal axis to the crest. That's the nodal axis here. Okay, so it's to the crest. Clear? Is that easy? Yes? Okay. So it has a structure. It has a speed. Does anybody know what the speed is?
Which one?
Light. That's what we're talking about. All light has the same speed. 3 times 10 to the 8th meters per second. Doesn't mean a lot to you, does it? Okay? The Americans in here, let me write it a different way. What is it in American? Look it up on the internet. Speed of light in miles per hour. Miles per second, sorry. Miles per second. Yeah, speed of light in miles per second. Will?
186,218 miles per second. 0.397.
186,000 miles per second. That's pretty amazing. 7 times around the Earth, ish. Yeah, it's pretty fast actually. Yeah. So all light travels the same speed. We have long wavelengths over here. Radio waves. We have microwaves. That's a micro. That's a Greek letter mu. Mu. M-U. Microwaves. How do microwaves work? Why do microwaves? Well, let me give you a hint. Here are here's visible light. Very small portion of the light spectrum. Okay? Look at this. The microwaves are much less energetic than red light. Why do we use them for cooking if they don't have much energy? Why do we use them for cooking if they're not very energetic? I mean, it doesn't make a lot of sense. It certainly doesn't make any sense to me. Well, it does now, of course, but when I first used the microwave or heard about microwaves, I was like, really? How does that work? Okay. You have water. Water has this bond structure. Hydrogen, oxygen, right? H2O, right? What am I doing? I'm like losing my mind here. H2O. No, I made a complete mistake. If you're going to make a mistake, do it well, okay? So you have these H2O, right? And you have these hydrogen-oxygen bonds, correct? Yes? Well, there's something about the structure of water that loves to absorb microwave energy. It's weird. And it makes them very energetic. Makes them bounce around and do all sorts of weird things. You've seen fleas do tricks. Well, water does tricks too when you irradiate them with microwaves. People pay good money to go in to see water molecules do tricks when they absorb microwaves. 5 dirham per ticket.
Oh my God, I can't afford that.
I know. I know, it's expensive, but I'm telling you. Water dancing because of microwaves, you've got to see it. Okay. So they become very energetic and it becomes hot. It becomes hot. And then the water getting hot actually cooks the food. So it's not the food that's getting hot. It's the water that's getting hot and then cooking the food. Kind of weird. You get it? Yeah? Okay. So there are other things that have these kind of bonds too. So it's not just water, but it's predominantly water. If you put something in the microwaves that is moistureless, it won't get hot. Take it out, doesn't get hot. Weird. Okay? All right. So microwaves are kind of weird. Let me tell you a quick story. All right, you ready? Ready for the story? All right. In Princeton, New Jersey on Route 1, it's actually not Princeton, but it's labs that are owned and operated by Princeton University. And these labs, this is going back many years. This is going back almost 20 years. I went to a workshop, a seminar, conference on the tokamak fusion reactor. Fusion is where, fission, you know fission. Fission you've heard about. You may not recognize the terms. When you split the atom, uranium, you give off all this energy, terrible radioactive byproducts, not very clean, not very good. What do we do with the leftover stuff? Et cetera, et cetera, et cetera. Bombs, blah, 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 blah. Okay. Then there's fusion. Fusion is where you essentially you take hydrogen and you make helium out of it. And it gives off neutrons and that slams into something and you create this heat from fusion reaction. Now, we can do a fusion reaction. We can do fusion reactions. Matter of fact, you know, the 100 megaton nuclear bomb is actually a fusion bomb set off by a fission bomb. I know the old ones were like the 1 megaton bomb. You know, the bomb that was dropped on Hiroshima in Japan was a fission bomb, a uranium bomb. And there was also a plutonium bomb. Anyway, and so when they made bigger bombs, believe it or not, they make bigger bombs. That was only a 12 kiloton bomb. Can you imagine? 12 kilotons. Now they have a 100 megaton bomb. And from what I understand, you need a fission bomb to make that work, because it takes so much heat to get the fusion started. Okay? And so how would they, and what you do is, there's this like donut-shaped reactor. It's three-dimensional. It's literally like a big donut. Yes? And inside the chamber, it's 300 million degrees. Very hot. Yes? Very hot. How do you get it that hot? How do you get it that hot? It's really hot. 300 million or 3 million. I mean, some outrageous temperature. Well, the way they get it is they put radio waves, they cook it with radio waves. And what you do with it is, it's called constructive interference. You take two radio waves and you put them on top of each other. What do you get? You get a bigger wave. So you do that enough and you get this enormous energy building up in the tokamak. Matter of fact, they would use so much electricity to get this going. Their electricity bill per month was $1 million. Then they had to cut back because it just wasn't as successful as it should have been. So those are radio waves. So radio waves can also be used to heat things. What you simply have to do is you add them together and you pump in a lot of radio waves that have the same frequency, and then you add them. Yes? Now, then you have UV rays. This is IR, infrared. This is UV, X-rays. And then you have, what do we have at the end? Somebody said it before. Victoria, what did you say? Gamma. Okay? Gamma rays. Right? You get it? Okay. So, those are the different rays. Okay? Those are the very general. This is very, very general. Well, where does all this come from? Where does all this come from? It comes from this. It comes from when electrons irradiate, something is irradiated, some kind of energy. Some kind of energy irradiates an atom. And the electrons jump. Well, what happens is if I irradiate this atom with energy, the electron's going to jump, and then it's going to go back to the level. So I irradiate it with an enormous amount of energy, much more energy than I need. But the electrons are only going to absorb a specific amount, a quantum of energy. That quantum is given off, and every atom will do it differently. For instance, strontium will give off red, and some blue. Okay, that's what strontium will do. So these packets are specific energies that are predictable. If I want to identify a material, I worked in analytical chemistry in industry before I went into teaching. And we used a type of spectroscopy that was very, very, very specific. It was called, I don't even know if it's around anymore, AUGER, Auger spectroscopy, Auger, that's what we called it. And what Auger spectroscopy was, let's say I have an electron being excited, and then it falls back down, right? Yes? And then the energy is given off, but it's absorbed by another electron. And then that energy is put back. And then that is gone. Do you see that? So there's a secondary energy. So I irradiate something, and it goes like this, correct? When it goes back, it gives off this energy here, right? And this energy absorbs it. This electron absorbs that energy, and it goes up and then back down. This is called a secondary. Now this is as easy as it looks. Let me ask you 3 very important questions, and if you answer them the way I think you're going to answer them, you'll understand this completely. Okay? Are atoms very organized in their structure and distribution of electrons? Are they? Absolutely. Tremendously organized. So, if an atom if you're a student and you're very consistent and you're very organized, can I predict your behavior tomorrow? Right? So if an atom is very organized, extremely organized, aren't I going to be able to predict its behavior every day, every minute, all around the world, right? And that's exactly what happens. Its behavior is very, very specific. So, is an atom organized? Yes. Can I predict its behavior? Will its behavior be unique to the particular type of atom that it is? Could that be true? And that's it. That's all there is. Therefore, I can predict if I have a substance and I irradiate it with energy, and it gives energy back to me, right? Different from what I irradiated it with, but it gives specific energy back to me. Do you think that that behavior, that specific generation of energy that was brought back to me, do you think that that energy is unique and predictable? And I might be able to take that and compare it to known behaviors and identify that substance? Do you think I could do that? Absolutely, and that's all it is. That's all we're doing here. This was just a much cleaner way of doing it. It got rid of a lot of the interference, because sometimes these electron transmissions are overwhelming and the instrumentation gets a lot of interference. Yes? So this was cleaner. You got a better indication of what it was. But that's all this is. Now, if you're being given light, does light have a wavelength? Does light have a frequency?
Yes.
Can I measure that? Probably. Okay. So if an atom is organized and it's giving off energy, and if that energy is light, could I measure wavelength and frequency of the light that's being given off? Absolutely. And that's exactly what happens. This light, you know what this light is called? You know what the light is called? Electromagnetic radiation, and it forms a continuous, it can form a continuous spectrum. For instance, the sun will give us all the different types of energies, from radio waves to gamma rays, and everything in between. Micro, infrared, visible, UV, X-rays, and everything in between. And that's what it's called. It's called electromagnetic radiation. Why is it called radiation? Why isn't it called something else? Why is it radiation? Because of how it behaves. Is the sun, by direct observation, is the sun hot or is the sun bright? By direct observation, is the sun hot or is the sun bright? It's bright. It's bright. Let's say you're in the middle of space, halfway between the sun and the earth. Okay? Are you cold? Yeah. Why? Because there's no matter between you and the sun that's going to warm and conduct heat to you, right? So you have the sun, you have the earth. This is the atmosphere. It's actually much smaller than that, but we're going to draw it very large, okay? You get this light coming through, you get these short wavelengths coming through. Yes?
Yeah.
What is that? What are those short waves absorbed by? Matter. The street, the black road, the air, the water, and then what happens to that heat that's absorbed by matter? Do you ever walk on a black road in the middle of the summer?
Yes.
Without shoes, bare feet? Hot, huh? So what's given off? What's re-radiated? It absorbs the light. It absorbs all the light, every kind of light, infrared, UV, visible, everything. And then what does it give off? It gives off heat. Okay? What has a longer wavelength? The light from the sun or the heat that's given off? The heat given off. This is a short wavelength. This is a long wavelength. You see that? So this wavelength bounces back to Earth. You see that? You get this short wavelength comes in. It creates this longer wavelength. The longer wavelength bounces back. It can't get out. No, help me! I can't get out! No! I'm stuck! No! Yeah. You know what this is called? Starts with a G. Green. 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 Green what? Greenhouse. Greenhouse. Greenhouse effect, right? You get it?
Yes.
You know what this is all about? What is this all about? What's this all about? Electromagnetic radiation spectrum. So we looked at electromagnetic radiation spectrum from what? electron transitions. That's where it all comes from. It comes from atoms. That's where it comes from. So, why do they call it radiation? Because it's not conduction. What's conduction? Touch the table. Feels a little cold, doesn't it?
Yes.
What does cold mean? Cold means what? No. Cold doesn't mean lack of heat. Cold simply is a sensation which says energy is going from my hand into the table. That's what cold means. It's describing a flow. That's what cold means. How many people never knew that? That's what cold means. Nobody knows that. It's weird. It's like Darcy is the only person in the world that knows that. So this is skin. This is air outside. I have such a sore shoulder, I have to hold it up. I have to prop my shoulder up. Don't get old, okay? See if you can find a pill that keeps you 16. Okay. If it goes this way, what's that called? What's that called? If it goes from the outside into your skin, heat. It's called hot, right? If it goes out of your skin, you're outside, it's negative 20 degrees and you're outside with very little clothes on. What do you feel? You feel cold. Cold. Once when I was in high school, never told my mother. I don't think I told anybody. I was like, I thought I'd get in trouble. I cut school. And it was like in the winter. And we had a challenge. So we drove down to the beach. It was like January. We parked. It was called Sandy Hook, this spit in central New Jersey. And the waves are just outrageous. I mean, you could literally be swept away. The waves were gigantic. And we stripped down to our bathing suits and we went into the water for like, 10 seconds. And we dove in the water and then we ran back out. We nearly froze to death. I was so cold because then we got to walk back to the car. We forgot towels. It was so cold. I've never been that cold before. I was that cold once again, but not that extreme. We were climbing up Mount Etna in the winter. It was really a hiking trail, and we took a bus up partway. And the wind was blowing. I got pictures, I'll show you. And the wind was blowing, and everything was horizontal, the snow. The wind was blowing, 60 or 70 miles an hour. It was unbelievable. And I just had running shoes on and a light jacket. And I wasn't that cold. I was cold, but not that cold. But my feet were freezing. And they started to get frostbite. And my friend sat me down. I took my shoes and socks off, and he rubbed them. You could hear me howling back on the Italian mainland. I mean, it was so cold. But that's what frostbite is. What's the difference between a burn from boiling bacon grease and frostbite? What's the difference? Absolutely nothing. It's the same. What does this heat do? What does that heat do? It dehydrates. If you lose enough heat, the water in your foot will freeze. Is therefore the water part of your foot? No, because the brain is saying there's no liquid water there. If the water is ice, that's the same as it being dehydrated. You get it? And you know what it feels like? You know what frostbite feels like, or the beginnings of the underpinnings of frostbite? You know what it feels like? It feels like you're dipping your foot into boiling bacon grease. It hurts so much. My daughter, I don't know when it was, but it was really cold outside, and she was home late, and my wife and I lost track of time. She was older, she was 16 or 17, and she was just walking home from her friend's house, like a mile away, but it wasn't that far, She's a teenager, she's 17. And she walks home, maybe 16, but she was over her friend's house. It was like we knew where she was, and it's a good family, etc. And she comes home. She walked home in her bare feet. She was crazy. Katie, you were nuts. You are crazy. I'm going to send this video to her. She was crazy. What was she thinking? Anyway, when she got home, she was in such agony. I made her sit on the edge of the tub, and I put cold water in the tub. First, we took her to the emergency room. They just sat her on the side, didn't do anything for her. I said, you know what? I can do that. So we left. And I brought her home, and I sit her on the edge of the tub, and I just had her put her feet in cold water. And she was howling. And you know what? There's utterly nothing you can do about it, because you have to thaw it off slowly. You don't want to thaw it quickly. If you ever get frostbite, don't use hot water, use cold water.
What happens if you use cold water?
You get burned. You get burned. Why? When you put heat into flesh, what's going to absorb the heat? Water. We're going to learn this later, Red, but water holds 10 times the amount of energy that iron holds. Isn't that amazing? If I have a pound of iron and a pound of water, the water can hold almost 10 times more energy than the iron can hold. It's unbelievable. So what protects you from excessive heat?
Water.
Water does, right? So if you're suffering from frostbite, if you're suffering from the beginnings of frostbite, what don't you have? You don't have the right amount of water, do you? Your tissue is becoming dehydrated, isn't it? So if you put too much heat in it too quickly, you can rupture blood vessels, do terrible things to your body. So you got to do it slowly. But she was howling. I thought my daughter was crazy. I thought she was crazy. And then all of a sudden, somewhere around 18, 19, she became normal. And she is the best mother. She has 2 kids, 2 grandchildren, just wonderful person. Wonderful. That's a picture on my computer, that's her. Unbelievable, but crazy back then. She was nuts. What was she thinking? But anyway, she was fine. She was fine. The feeling came back, and it took a couple of days, but she finally was normal again. But anyway, so that what kind of transfer of energy is touching? That's contact, conduction through contact. Yes? If you heat your home, you heat it through convection. I heat the air at the bottom on the floor. I heat the air, right? Or hot air comes out the vents, and what does it do? It rises, cools, falls, heats, rises, cools, falls, heats, rises, cool, falls, heat, right? So you're heating through what? What's that called, kind of heating called? Or cooling, what's it called? Starts with a C. Convection, is that what you said? Convection. So this is heating through radiation. You don't need matter to conduct the heat. You don't need matter to conduct the heat. You can conduct, Mr. Asher, you can conduct without matter. It's called radiation. Clear? All right, we're done. Spectroscopy we talked about, right? So that's another word we can cross off. What's spectroscopy? Anybody want to put it in words? It's analyzing the electromagnetic radiation spectrum given off by matter to define or identify that matter from the specific energies it gives off. Is that good? Is that well worded? Okay? We're off.